Hello everyone and welcome back. In the last few videos, we discussed the CAP theorem when it comes to building distributed systems in relation to databases. This is an extension of those topics on CAP theorem, where we're going to talk about acid and base properties when it comes to database selection, and it builds upon what we learned in the CAP theorem. So let's start with acid. Acid, ACID, are four different properties unique to an acid database, starting with A, which is atomic. When thinking about an atomic database, what it needs to do is it needs to ensure that these transactions are atomic. Now, what does that mean? Well, we know that with a transaction, there might be multiple records that are being modified. Maybe new records get added or deleted or updated, but the idea is that a transaction might touch multiple records in the database. In this particular case, if we were to remove $100 from Sarah's balance and then add $100 to Matt's balance, this is one transaction where we're transferring $100 from Sarah's account to Matt's account. This is one transaction, but there are two records that are being modified here. Sarah first will have to remove $100 from her balance, going down to $900. Matt, on the other hand, is another record where $100 is being added and his record updates to $100. In this case, this is what the transaction needs to do in order for it to be considered complete. But let's say that during this step, the first record, Sarah's $100, gets removed from her balance, going down to $900. But then when it's time to add the $100 to Matt's balance, the system encounters a bug, or the database encounters a bug. In this particular case, that $100 does not get added to Matt's account. What happens in order for this database to be considered atomic is it must roll back all of those values that got changed before this transaction began. So what will happen is that Sarah's $900 gets reverted back to the 1,000 as if that first step of the transaction never happened. In this case, in the event that any of these steps fail and all of the records that need to be updated don't get updated, if any of that happens, then it all rolls back as if that transaction never happened. Only if we're able to ensure that all of the appropriate records get updated in a transaction in order for it to be considered complete. If that happens and if the database guarantees that, then is this database considered atomic. So that is the A. Next is the C, which stands for consistent. We already learned about consistency. Consistency in this case is just that between every transaction, the database and all of its nodes are consistent in data, as well as all of the database is not falling victim to any bugs or any violation of the rules that govern the database, which makes it structurally sound. This means that in order for a database to be consistent, it must satisfy this value. Every transaction that happens does not compromise the structural soundness of the database itself and all of its subsequent nodes. Next, we have I, which means isolated. So in order for isolated, let's go back to talking about transactions inside of our database. Let's imagine we had two transactions that were happening around pretty much the same time. One is the Sarah account getting credited $100 and then Matt getting debited the $100 in return. The other transaction is that we want to count the total of all the accounts. And let's say inside of our database, we only have Sarah's account and Matt's account. In this case, what happens is that let's imagine that Sarah's account first subtracts the $100. So in this first step of the transaction, Sarah loses the 100 and that balance updates to 900. But let's say before the Matt debit happens, our other transaction, count total of all accounts, runs. In this particular case, the Matt balance has not updated, but it's still going to read the total of all of the accounts. And what is that total when you add it together? Well, it's $900. But in this particular case, our transaction on the left has not finished yet. So what we're doing is we are peering into all of these different accounts in the middle of a transaction. So the state where it's incomplete. And in this particular case, this $900 is incorrect because we know that Matt has yet to be debited the $100. So here, this is not isolated. In order for it to be considered isolated, what has to happen is that the count total of all counts, regardless of when it runs, if it's running alongside this transaction on the left, it needs to count before the value actually happens, meaning that it will count when Sarah has $1,000 and Matt has 0, hence giving us the total of 1,000, or it has to happen after that transaction happens, meaning that Sarah's account gets updated to 900, Matt gets updated to 100, and then the count total runs, and it will see and add these values together, again yielding 1,000. So isolated means that the transactions are unaware of the in-between states of the other transactions. This almost makes it seem as if running all of these transactions side by side, that it happens in a sequence. This might not happen in how the database actually runs all of these transactions, but the key point here is that the transactions cannot peer into the database when another transaction is in the middle of updating the state. Isolated pretty much means that these transactions are isolated from each other. They cannot get involved in the middle of another transaction. That's isolated. And then D is durable. And durable just means that in the case that your database goes down, it does not roll back to any value if any transaction has already completed before. Meaning that if a value has been updated from a transaction, if that database goes down due to a bug or an error or whatever, it will not roll back any values to a previous value. Again, this only makes sense if those transactions are considered complete, meaning that if they're atomic, they are considered complete as well. So durable just means that the changes that get made by complete transactions persist regardless of whether or not that database goes down. Now, databases that have this ACID property are pretty much uniquely relational databases or SQL databases, which you've learned throughout that SQL course that Mo and Andre taught. If you think about a need for a database that is ACID compliant, you need a SQL database when you want these exact properties. If you don't need ACID, then you are looking for a base database. Now, base is not as pretty in the mapping of what it represents to ACID. Base stands for basically available, soft state, and eventually consistent. Now, basically available means exactly what we learned about with availability when it came to CAP theorem. It just means that if you are getting a request to a database, you always return data regardless of whether or not it's fresh or stale. Soft state is a reflection of eventual consistency. It means that the state of your data is soft or in flux. It's not hard. What this also means is because it's tied to eventual consistency is that when you think about a system that prioritizes availability, we mentioned before that maybe there's partitions or maybe there is a slowdown in actually updating all of the nodes to reflect the same state. That is not consistent because it prioritizes showing data regardless of stale or freshness of that data. But it doesn't mean that we don't want that data to become consistent at some point. Eventually consistent means exactly that. Eventually, these nodes will be consistent in the data. It's just not the priority. So as a result, our state is in a soft state because that change might happen at some point. We just don't know really when. It's not driven by the input. In an ACID-based system or database, whenever input comes in, meaning whenever a transaction occurs, the state will pause and lock until all of those nodes are up to date with the same state, which is a hard state. A soft state means that these nodes are in flux. They'll still return values. It's just that at some point they'll become consistent, but the state is in flux. So the whole way to think about base is really just that it is eventually consistent, but pretty much as available as possible as long as nodes are up. That is base properties. So a base-driven database is a NoSQL database. You might be talking about Cassandra, you might be talking about Redis, you might be talking about MongoDB. These are all NoSQL databases, and they are all base compliant. So that's really it. ACID for SQL databases or relational databases, base for NoSQL databases. And that is ACID versus base. Now again, choosing an ACID or a base-based database will be dependent on what you need your data to be. If you're working with financial institutions and transactions, you're most likely always going to want a relational database because you need to prioritize consistency in your data. If you're talking about anything else like messaging apps, where you just really need the data to be available, but you don't really care whether or not that data is stale or fresh, and yeah, you might care that eventually the data is consistent, then you would pick a NoSQL database. The whole idea with availability over consistency is that this availability scales quickly and fast. Whereas you can scale relational and SQL databases, it's just a little bit more challenging because you need that consistency. And that's pretty much ACID and base as well as cap theorem when it comes to database considerations and choosing them in your system design.